For today, what I want us to do is I want us to just go through the theory side to Unit 2. That's what I'd like us to do. So we're just going to go through the slides. Then next week when I see you, we're going to obviously do the exercises for Unit 2, right? And then obviously you guys will be ready now for your test 1. Okay. So let us go there. Okay. All right, so your Unit 2, all right, is on algebra. Okay, I'm sure we've all seen or know or have experienced what algebra is all about, okay? But as a basic definition, algebra is the area of mathematics where letters and other symbols are used to represent numbers in equations and formulae, okay? Right, that's pretty much what it is in a nutshell, okay? And I think sometimes we attach too much to these things. So it's like, algebra. It really is where we're just introducing letters in place of numbers, okay? And I think the reason why we do that is simply because we actually don't know what the value is of that particular amount or number, all right, that's being replaced with a letter or a symbol. Does it make sense? So since we don't know what it is, that's why we call it A, or we call it X, or we call it Z, all right? Then it goes on to say, substitution, right? Basic rules of algebra. First one, substitution. That means substituting a numerical value into an algebraic expression, okay? All right, then it says here, consider the following expression, x2 plus 5x minus 7. If we want to determine or evaluate the value of the expression for x, all right, x is equals to 4, all we have to do is substitute 4 into the expression, okay? So when we now know what x is, then we can finally calculate what this is obviously equals to, okay? Right. Then, secondly, expanding brackets in algebra, all right? If there is a numerical or algebraic term in front of a set of brackets, okay, obviously what must we do? If there is something outside the brackets, we have to multiply, okay? Same principle here, we also have to multiply, okay? We simply have to multiply, okay? Right.
That example in the number.
Which one? This one? Second one?
Top one.
Top one. You say it's confusing what?
Well, 3 times in brackets 18 minus 5 is not 39.
Okay, so let's do this. 3 times 18.
No,
Okay. Happiness.
Yeah.
Okay. All right. Perfect. Then let's move forward. Okay, then the next rule that we have there is factorizing an algebraic expression. Okay, factorizing is the opposite of expanding, so already we then know exactly what happens with factorizing. And the way I saw factorizing, we used to actually call it simplifying. I don't know if any of you guys used to call it that.
Yeah.
Okay, and that's pretty much what you are doing. You're now taking something that has been expanded, and now you are making it simplified by way of getting your brackets back, okay? All right, in the above example, each of the terms in the initial expression have the common factor 3a, okay? Whenever we're simplifying something, we need to look for the common factor with which we can divide and therefore obviously simplify the expression or equation, okay? All right, failure to do that, then obviously we can't simplify the actual expression or fraction or equation. All right, then simplifying an algebraic expression. Before looking at examples involving the simplification of an algebraic expression, students should first be aware that algebraic expressions can be grouped into three different types. Those that can be simplified immediately without any preparation, those that require preparation before being simplified, and then finally, those that can't be simplified at all. So sometimes, guys, you can't simplify, and they'll be testing you to know when, do you know when you can't simplify something, okay? Obviously, that will speak to you, you know, your knowledge on, are you able to find like terms? If not, then you know you just leave it alone. If you can, then you can obviously simplify. All the following examples represent expressions that can be simplified. So obviously, just need to refer to the page to see examples, okay? Then equations. An equation is a statement indicating the mathematical equality of two expressions, okay? For example, all right? Here you can see whatever is happening over on this side is obviously then equals to, okay, right? In the above equation, the x is called a variable or an unknown. Remember what I said earlier? The reason why we're introducing letters is because we don't know the actual value of x, okay? Right, but fortunately for us, that's the only variable that we don't know here. So since it's the only variable, we can figure out what x is, okay? By obviously throwing the 3 to the other side. Once we throw the 3 to the other side, it becomes what? It becomes 4, yes, because it's a plus 3, okay? Then we know that 2x is then obviously equals to 4, right? And then what must happen? Divide both sides by 2, okay? And then x is going to be equals to, and you're done, okay? Right. All right, and there they're just saying that the 3 and the 1 are referred to as constants. Solving an equation means finding the value of the variable that makes the equation statement true, okay? Which is what we just did, okay? So that's always your objective. If you have more than one variable, okay, then obviously you're going to end up having an answer which is going to include variables. Does that make sense? Unless they actually tell you x is equals to 3, and then they leave out what a is equals to. That means that you will first have to substitute x with, I've forgotten what I said x is equals to. It's equal, you will substitute it with 3. Once you've then done that, then you can calculate what a is equals to, okay? All right. And then we also calculated x to be equals to 2. All right, then the fourth thing, they say solving algebraic problems. Rule 1, the same number may be added to both sides of the equation, okay? That's actually what must happen. Okay, what you do on the one side, I'm sure you guys have heard this before. What you do on the one side, you have to do on the other side, okay? The second rule, the same number may be subtracted from both sides. Okay, still covering that same rule, okay? What you do on the one side, you have to do on the other side. This is the thing about math, and this is why I like numbers more than I like theory. It's because the principle remains constant. I can't tell you today that 5 plus 5 is equals to 8. Okay? 5 plus 5 is equals to 10 when you're in grade 5. It's going to be equals to 10 now, and it's going to be equals to 10 when you guys leave this place. Okay? So the thing about, for me, what I began to realize is that as long as I understand the principle that needs to be applied, and I'm capable of applying the principle, all right, which I know all of you are, then I'll be just fine, okay? So that's what, for me, I then sought out to do, just to understand what is the principle, how do we approach solving the problem at hand. Okay, both sides of the equation may be multiplied by the same non-zero number. Okay, so here they're pretty much just repeating the same thing. All right, like I said, whatever we do on the one side, we must just do on the other side. Okay, finding the unknown value in a formula. Okay, a formula is an equation in which the terms are represented by words or symbols. If we know the value of all the terms except one, then we can determine the unknown value using substitution. Okay, right. So guys, you'll see this in accounting, you'll see this in mathematics or stats, right? You'll see this in everywhere where there's pretty much numbers. Finance, you'll see the same thing. They'll give you just enough information for the other variables, and then you have to calculate one variable, okay? If revenue is 10,000 and expenses are 3,000, then substituting these values into the above formula gives you 7,000. Okay, pretty straightforward. Nothing too hectic there. Then changing the subject of a formula. Okay, this is pretty much straightforward. Like whenever we're given a formula, right? For instance, on the last page, it was income minus expenses is equals to profit. Okay, sometimes we're not actually looking for profit. We might actually be looking for our income. They've told us you made a profit of 5,000. They've told us that our expenses were 3,000. We can obviously then work our way back to find what our income it was. Okay, so it's always about what is the question actually looking for, and then obviously using the formula, manipulating the formula, and that's what we are now calling changing the subject of the formula to obviously answer the problem or solve the problem that you're obviously looking at trying to address. Okay, that's pretty much what solving, changing the subject of a formula is about. Manipulating the formula that you've been given to obviously speak to what you're trying to achieve. Sorry?
Can you use the triangle?
Triangle? What triangle are you talking about?
What is the terms you can put it as this?
Okay.
Price,
Oh, okay. And then?
quantity.
And then revenue. Okay, so let me do that triangle and then just explain it for us. Okay, so this is what he has. Up top is revenue, right?
Yes.
So here you got revenue, and then here you have
On the left hand side, you have profit,
profit, and then here
quantity.
quantity. Is it not price, this P?
Price.
Okay, okay. I thought I heard you say profit. Okay, but that's fine. So yeah, this is just another way of obviously highlighting that which is on the board, okay? Which I'm seeing for the first time.
No?
I'm seeing for the first time. I'm not saying it's wrong. It makes total sense.
When you're calculating
Revenue times price and
the
quantity.
then when you're looking for a quantity, it's revenue
Divided by
price.
Ah, okay. All right, and also if you wanted price, then you just divide revenue by quantity, right? Okay. That's awesome. Okay. I don't know where my teachers were when you were learning this stuff. Okay. All right, so that's just another way that we can obviously do the formula there. I think it's a whole lot easier to remember. All right. But let's proceed. Okay. Solving inequalities in algebra. Rules for solving inequalities. For the most part, the same rules that we have previously learned for solving algebraic problems can be applied when solving inequalities. However, consideration must be given to how the inequality sign is affected by the application of these rules. Okay. The additional guidelines given below should be followed. Adding and subtracting the same value to or from both sides of an inequality does not change the inequalities in the inequality sign. Okay, multiplication or division both sides of the inequality by the same positive number does not change the inequality's sign. Okay, then multiplying, dividing both sides of the inequality by the same negative number changes the direction of the inequality. Okay, I think some of these things we probably still remember from school. Okay, but basically, and forget these two, and just remember that when we multiply or divide by a negative number, it's going to change the direction of the sign. I think it's easier just to remember that one as opposed to trying to remember these other two, when all we need to remember is that this changes, these others don't. Make sense? Cool. Then linear equations. Okay, now when it comes to linear equations, what are we trying to assess? We're trying to see, is there a relationship between two variables? Okay, relationship. Whenever you see linear equation, you should be thinking, is there a relationship between the two variables? Okay, in the situation where this relationship can be described by a line. Okay, right. Two variables consist of an independent variable, okay, and a dependent variable. I'm sure this is nothing new to you guys, so you guys tell me, what is a dependent variable? What is an independent variable?
When there's a number in front of the alphabet. Dependent.
Okay, that's his response. Yes.
Independent variable is when it can stand on its own.
Uh-huh.
Like that's when
Your English bundles is finished.
It's when it can stand with others. Reminder, for example, it's example even numbers are
Okay. Okay. Anybody else? What do you think a dependent and independent? I feel the answer's in the name, and I think you alluded to it quite a bit.
If it's on like a table.
What is that? Independent and dependent? Well, for now, I'm just thinking about the concepts between what would make something an independent and what would make something a dependent variable.
not X and Y.
X and Y, yeah, we typically get to that. Let's see if they actually include the formula. So here's your formula for a line, the thing I underlined in red. So there you can actually see the breakdown. It says Y is the dependent variable and X is the independent variable. B is the slope or the gradient. I'm sure some of you are going, oh, I remember this before. Okay, now, I think school education is more fun when you can see practical examples. So let's think. Remember, when it comes to independent and dependent, we're thinking about relationship. Linear equations, we're thinking about relationship between two variables. So somebody tell me, is there a relationship between fuel and inflation? What's the relationship between fuel and inflation? Yes.
For example, the inflation was to go up.
Uh-huh.
It automatically goes to
Which one usually goes up first? Fuel or inflation?
Fuel.
Usually fuel goes up first, then everything else, then inflation follows. Right? All right. So which one then is the dependent and which one is the independent?
The inflation is
The independent is the?
Inflation.
Okay.
And the dependent is
And the dependent is the fuel.
No, the other way around.
The other way around.
independent the fuels and inflation.
I like that idea. I like that idea. Let's vote.
Yeah.
Who says the fuel is the independent? Okay. Who says the fuel is actually the dependent? No one. Absolutely no one. You didn't all vote though. Okay, then absolutely no one is correct. I'm joking. You guys are actually right. So the fuel is the independent. Why is the fuel the independent?
Because it changes first, and then it doesn't rely on inflation.
100%. It doesn't rely on the other variable, which is inflation. Okay? It is what actually causes the change in inflation. Does that make sense? Okay? Particularly pertaining to our example. Okay? As you guys said, sometimes you can have inflation and then the inflation will actually influence the fuel to go up. For instance, because now, obviously fuel needs to be transported by trucks, right? So now if your tires cost more, your wages go up, your, what can I say, maintenance on trucks goes up, then obviously the supplier of fuel will also say, I'm going to up the cost on my product, which is obviously the fuel. Does that make sense? So you can have that, but obviously for the scenario we illustrated, we were saying that it's the fuel that goes up and then the inflation usually follows, which is typically what happens in life. But the whole thing that we are trying to illustrate is the independent is the one that, regardless of what changes for the dependent, it will not influence the independent. But if the independent changes in any way, it will obviously influence the dependent. Okay? Does that make sense? Okay? And that's why this formula will then explain to you or show you whether there is a relationship or not. Because what we're saying is X, right, is the independent. So we're saying that, and D is the gradient. Remember, we are usually looking at a graph, all those lines, and we do the whole x-axis. So let me actually just, this is typically, and we have the x and we have the y, okay? Right. And then what we are saying is, this is typically our line. We're saying if initially fuel is 5 Rand, right? And then we put it up to, let's say 10 Rand, okay? Does that change the price in Y? Okay? And there, this is the price in Y. Bless you. So here's 15, and then let's call this 25. Okay? Then obviously the gradient is the steep of the slope. So that is B. Okay, and then A is the intercept. Okay? So that's where those two lines meet. Okay? Right. So that was just to give you a graphic representation of what we are actually doing here. But the key thing that we want to take away is that we're assessing a relationship and we understand the nature of what an independent variable is, what a dependent variable is. Okay, then obviously we need to know that formula. Okay, but let's proceed. Okay, the format of a linear equation. When drawing a graph of a linear relationship, the following should be kept in mind. The horizontal or x-axis displays the values of the independent. The vertical y-axis displays the values of the dependent variable. Okay. What is that word? Scales.
Yeah.
I was thinking.
Is our question going to come like this?
No, this is not. It's not going to come like this. We wouldn't ask you all this information. We'll just probably ask you to either do the graph or calculate the linear equation. something to that effect. Yes, you're saying? Okay. Then it goes on to say scales should be chosen for each variable so that the graph does not look cramped. Okay, the scales should be clearly stated. Okay, this is nothing new to you guys, I'm sure. Graphs should be neat and easily interpreted. All right, the graph should have an appropriate descriptive title, and if relevant, the source of the data used to construct the graph should be indicated as well. Okay, right. All right, so how do we actually draw these graphs? We need coordinates. Okay, once we have the coordinates, then we can obviously draw the line. All right, and then we see which points does the line go through. All right, we find the linear function or equation for the line that goes through the coordinates. All right, using the following steps. Obtain the value for b by inserting the values from the coordinates into the equation. Okay, basically there we would then be assessing the change in the variables. So can you see here, we're subtracting y2 from y1. Okay, because y1 is initially where we were. That was our initial point. Okay, then we're subtracting it from y2. All right, and then we're dividing it by x2 minus x1. In other words, also the change in the independent variable to see what is the impact that we are then having, right, on the dependent variable, which is y. Does that make sense? Okay. Substitute the value obtained for b and the x and y values for either one of the coordinates in the linear function format, y is equals to a plus b, x, and so for a. So in other words, what they're trying to tell us is that once we now have b, we can then use any of the coordinates. We have to pick whether we're going to use x1 and y1, okay, in the formula, or whether we're going to use x2 and y2 in the formula to find a, okay? But you have to be consistent if you're going to use the first coordinates or the second coordinates, okay? Then finally in C it says the linear function for the line is then y is equals to a plus bx with the values obtained from the above procedure substituted into the expression for a and b. Okay, cool. Then it's speaking about simultaneous equations. Okay, when dealing with two unknown variables, two simultaneous equations are required to obtain are required in order to determine the values of the two unknown variables. Okay, now you can solve simultaneous equations either graphically or algebraically. Okay, I like to do it algebraically. In all honesty, I like to use substitution. I don't know, sometimes graphs just can confuse one. Okay, but either or, you should be just fine. Okay, and then here they're obviously talking to the procedure of how you do it graphically, which is pretty much like how we're doing the whole linear equation type thing. Okay, and then finally we have solving simultaneous equations using substitution, which is my first choice, if possible, is to just do it via substitution. Okay, all right, so there you also have the steps. Okay,
which is which? Which is which?
So here on the first slide here, it's the steps to solving it graphically. Then this is the steps to solving it via substitution. So this is assuming that you have the answers to maybe, let's say, x. If you know what x is, then you can obviously work out what y is equals to. Does it make sense?
We introduce the two equations. Is there going to be two equations for each?
So typically they'd give you what would happen is maybe they'll give you two equations, right? Then you will look at your graph to say what are the points, okay? And then you would use those coordinates to substitute either into x or to substitute into y, right? Then when you substitute into y, for example, you will then solve for x, okay? If you substitute into x, you will then solve for y. Once you've solved for either one of these, when you now know what x is or when you now know what y is, then you can work back to find out what x is equals to or what y is equals to. Does it make sense? That's how you then do the whole substitution type thing. Then you have elimination. Then you have elimination, and then here now they're speaking to non-linear equations. A common non-linear equation is the quadratic equation, which has the following format. Okay, graphically, a quadratic function takes the form of a parabola. Say it again. Parabola. Okay. That's what I thought I said initially. That thing. That one.
The one that goes like this.
Yeah, I think so.
Like this.
Okay. Yeah, eh? All right. So that is your theoretical side to your unit 2. Okay. Like I said, I have an ice task for you guys to go and do.